So let's now move to the examples part of our discussion on the first law of thermodynamics. The discussion on the examples part is divided into two parts. So you have examples part 1 in this video, and then in the next video we'll cover part 2 of the examples. So let's now have example 1. You have an ideal gas which undergoes an isothermal expansion at temperature T, during which its volume changes from V1 to V2. How much work does the gas do? Express your answer in terms of pressure. So isothermal process, the temperature is constant. So initial temperature is the same as the final temperature T2. So let's just have temperature T. Expansion, therefore the initial volume is less than the final volume. Assuming that the pressure that the gas applies is not either experiences or applies is not equal to 0, work done by the gas is equal to integral of P dV from initial volume V1 to final volume V2. Okay? Since we cannot say that the pressure is constant, we'll have to leave the pressure P variable inside the integration process. And indeed, for an ideal gas, we can apply the ideal gas law. PV is equal to nRT. We can isolate P, which gives us P is equal to nRT over V. We have expressed our pressure in terms of volume V. So if we plot in this equation of pressure into the equation of work, we get the following equation. Work is equal to nRT integral of 1 over V dV from initial volume V1 to final volume V2. Integrating 1 over V dV, we get ln of V2 over V1. So work done is now equal to nRT ln of V2 over V1. Now this is the work done by the gas as it expands from initial volume V1 to final volume V2. The problem asks us to express our answer in terms of pressure. If we go back to our ideal gas law, PV is equal to nRT. For an isothermal process, PV is equal to nRT is equal to constant, meaning PV is equal to constant. So PV in initial state is just equal to PV in final state. So P1 V1 is equal to P2 V2. Rearranging, we can get V2 over V1. V2 over V1 is equal to P1 over P2. So substituting into our equation for work, we have our final answer. Work, W, is equal to nRT ln of P1 over P2. The next example, example 2, is an application of what we covered here in example 1. So let's move to example 2. During the time point 305 mole of an ideal gas undergoes an isothermal compression at 22 degrees Celsius. 518 joules of work is done on it by the surroundings. So, during the time that the gas undergoes isothermal compression, 518 joules of work is done on the gas by the surroundings. If the final pressure is 1.76 atmospheres, what is the initial pressure? So, 0.305 moles of the ideal gas, that means N is equal to 0.305 moles. The temperature is constant, isothermal. So, constant at 22 degrees. T1 is equal to T2 is equal to T is equal to 22 degrees Celsius. Let's convert that to Kelvin, which gives us 295.15 Kelvin. The work done is 518 joules. This is work done on the system by the surrounding. So applying our sign convention for work done on the system is negative. So work is equal to minus 518 joules. And the pressure, final pressure, so P2 is equal to 1.76 atmospheres. So applying what we learned sa example 1, in example 1, PV is equal to nRT, isolating P is equal to nRT over V, substituting this into our equation for work is equal to integral of P dV from initial V1 to final V2, substituting and integrating, work done is just equal to nRT ln of V2 over V1. Again, isothermal, so PV is equal to nRT is equal to constant, which gives us P1 V1 is equal to P2 V2. Rearranging and substituting into our equation for work, we have work is equal to nRT ln of P1 over P2. If we now look at the known values, all the variables are known except for initial pressure P1. We are able to calculate P1 to be 0.881 atmospheres. So that's it for now. And as mentioned, we will cover the second part of examples for first law of thermodynamics in the next video. Thank you for watching.